Yeah, so we're gonna look at section 3.6 today. Before we do that, we've got some things we need to talk about as far as our schedule. Very good. Let's see. So we're closing in on time for test 2. Yeah. So we've got 3.6 we'll do today, and then 3.6 is today. It's not a bad section, so we shouldn't have any trouble getting through that today. And then we kind of have some combined stuff out of 3.7 and 3.9. It's really more related to 3.9. That will be our last section, and then we need a review. And then we need a test. If we just did all that, that would put us, that would put test 2 on March 4th, which is a little quick, I think. Okay. That would be next Friday. Okay. That's a little bit quick, I think, considering how much we've covered. So my thinking is we need to, somewhere in here, either here or here, need to put a web assign day. Because we can. We're not going to get behind if we do that. At least. So I say we push that. That'll push us to either. March 7th, which is a Monday. Or Wednesday, March 9th. That's for test 2. Okay. So I don't really care. It doesn't matter to me. We've got time either way. Okay. We're doing good on the scheduling here, so I think we'll just take a vote. You're the ones here today, so you're the eligible voters. Okay. If somebody's not here, they're just stuck with whatever we decide. Okay. So I think take March 4th off the table, and then decide do we want to do a Monday, March 7th, or Wednesday, March 9th. Okay, both of these we get a web assigned day in at least. If we decide to do March 9th, we might take 2 class periods here, kind of stretch that out a little bit, go a little slower, and then throw a web assigned day in there. Okay. So normally I would do show of hands, but I think maybe just for the heck of it, but I think I kind of want to do secret ballot. Okay, for vote here. We'll see if it comes out different than I think it would if we did show of hands. Okay, so I got an idea of what the vote will be, but okay. So get your little piece of paper. It doesn't have to be big, just big enough to write either the 7th or the 9th on there. So this is, let me make sure. This is a Monday. This is a Wednesday. Okay. If anybody needs a little piece of paper, I'll be glad to give you some of my yellow paper. Let's see. No, you don't have to put a name. That's a secret ballot. Yeah, you can put somebody else's name if you want to. As long as you don't put your name, it's still secret. Yeah. Okay. So
if we do it tonight, then we'll get on Friday for web assign.
Well, I don't know. We can talk about that after we pick the day, where exactly what order we want to do web assign or review in. We can flex that around too. Okay. We have the ability, so we might as well be a little bit flexible. Can't get this. All right. Everybody got your vote decided? I'll come around and get them, and then we'll do like a live tally. We'll keep track. And then doing it this way, I can just write down whatever day I want, because you can see the ballots. Thank you. It looks like everybody voted. Thank you. I won't do that to y'all. Yeah. Thank you. There, thank you. Be a little slightly more entertaining to do it this way. Thank you. So let's see. I got a 7 pile and a 9 pile. Let's see. I'm gonna shuffle them up so you can keep track. So let's see. Here is let's say how many of us there are. We can decide if we'll get a majority. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So 9 would be majority. Let's see, there's a March 9th. Make sure I don't double count any. There's a 9th. It might not take long. Ooh, there's a 4. Cute. There's a 7. Hope they didn't need that vote. Oh, there's a 9. Yeah. There's a 9. Some of these will take me a second to unfold. You know there's a maximum number of times you can fold a piece of paper? You ever thought about that? Yeah. Maybe. Like a huge piece of paper, yeah. No, it's one paper, but it's like stuff. Yeah. Yeah, to try to break how many times you can fold it. So the problem is it gets thick. So you would have to have a really big piece of paper. So when you fold it, it's like thin compared to how big the paper is. So there was a 9. I think I counted that one. There's a 9. Shocker. There's a 9. I got a whole pile. I only need one more. All right, there's 9. So there's the majority there. Let's see. 9. 7. 7. 9. 9. So as expected, sorry, 7 people. All right. So now let's think this through. Okay. So 9's our winner. Okay. So let's see. 3-6 today. Start working on 3-7, 3-9 Friday. Let's do some more 3-7, 3-9 Monday. So then web assigner review. I don't care which one we do, what day, but let's get the calendar out here. So Monday the 7th, we'll finish up 3-7, 3-9. Okay. Since we're doing that, we can also not take the whole hour and a half Friday, so that helps too. Okay. So finish up 3-7, 3-9 Monday, and then either where I'm at Monday. Okay. So then either what do we got left? Hang on. So then we've got a web assign, a test review. So we really got 2 days doing it that way. Right? So all right, 28th we finish material. Let me just write them down. So then we got the 2nd, 4th, 7th, and 9th. Okay. So, we really kind of ended up with an extra day that I miscounted somehow. So which one? So this is test. Which day do you want to do review on? You want to do it right before the test, or you want to do it a little bit earlier so you have more time after the review between review and the test? What do you think? Earlier review or later review? Earlier. Okay, on the 4th maybe. Okay. We'll do review there. So let's see, what did I? Oh, okay. So I already had Friday and Monday planned for 3739. So we get an extra day in there. That's okay. So which day you want to do WebAssign day? The 4th's Friday. You want to? Okay, all right. All right, we can back out that. So we want to do WebAssign here. Review on here. Okay, so does that look okay? Okay, so we'll do. I'll do a bonus problem assignment in WebAssign, and if you want to, I'll give you some help on those on the second. How about that? Do some of the maybe a little bit messier ones or something like that that we didn't put in the regular assignment. All right, so there's our plan then. And then just a heads up, test 3 will not take us as long to get ready for it. And chapter 4 is a little bit shorter. And so test 3 will probably be the Friday after spring break. So we'll have 4 classes before spring break after test 2. And then and come back and have a couple classes and then test 3. So a little bit shorter, just kind of don't want it to sneak up on you on that one.
Do we have a final?
Yeah, got a final. Yeah, it's not as bad as it sounds because really when you back out and look at the big picture, we've got like 2 topics in here. We've got derivatives. Well, we had limits, so you could say 3. We got limits, derivatives, and then the stuff that'll be on test 4 intervals. So it's not horrible. I think some of the limit stuff, maybe you forget some of the limit stuff, but then with the derivatives, when we start doing intervals, you really kind of have to remember the derivatives. So it's not that bad. It's not like a comprehensive history final or something where you just have to remember everything and you never use it again. All right. Okay. So, and I think we'll still probably have enough room to do maybe one more WebAssign day somewhere in here before the end after spring break. So we're doing good on the schedule, so we're not rushed. That's good. Okay. All right, so again, short set of slides, and then we'll just do some example problems in this section. Okay. So we've got one other set of derivative rules to learn, and these are actually not bad. Okay? And that's taking the derivatives of the logarithms. If we have logarithms involved. And then once we do that, once we learn how to take the derivatives of the logarithms, there's a technique that can be used, doesn't necessarily get used a lot, but can be used to take derivatives of complicated looking functions. and then we'll talk about using logarithms. Okay, so we'll talk about both of those. Okay, the main target in this section is for you to get the derivative rules for taking the derivative of something with a logarithm. Okay. All right, so a little bit of review, and then we're going to do some review of logarithm rules too. Okay. But if we have a logarithm, the basic shape we have, right, it approaches negative infinity as x approaches 0 from the right. Okay. And then as x approaches positive infinity, our limits actually goes to positive infinity. Okay, it keeps getting bigger and bigger forever. There's no bound on it that way. But when we're looking at a log, it looks like really, really flat. Like this x-axis is really, you would have a lot of numbers between there for it to look like it's going up that much. Logarithms look like they're almost horizontal, okay, when they get on over past 1. So they grow really, really slowly. And you can kind of understand the reasoning for that if you remember that logarithms are the inverse of exponentials. So exponentials grow really, really quickly. So their inverses grow really, really slowly. So exponentials, when you hear things like exponential growth, you hear people freaking out talking about like COVID, we're in the exponential growth phase, things like that. And that's saying their cases are growing, increasing really quickly. Logarithmic growth is the opposite. Okay, it grows really, really slowly. And then depending on how good of an algebra teacher you had, you might not talk too much about logarithms. But the main purpose why logarithms started being used is because of their properties, where we can take like multiplying big numbers and rewrite them in terms of logarithms, and then we can do addition instead of having to do multiplication. Because especially if you have big numbers, it's a lot faster to do addition than it is to have to do multiplication. You can think about doing the longhand on a piece of paper there and see that that's true. Okay. That's kind of outdated because pretty much any numbers we want to multiply now, we can use technology, we can use software, and it's not that big of a deal for software to do that big multiplication. So the reason why we still care about logarithms, okay, so from a pure math side of things, logarithms are cool, so they have really neat properties. But from a practical standpoint, anytime we have something that gets bigger really quickly, we can take a logarithm and it flattens it out. So we do have measurement scales that we use the logarithmic scale for. So things like the Richter scale, if you're measuring the magnitude of an earthquake, that's a logarithmic scale. So like if you have a magnitude 3 earthquake and a magnitude 2 earthquake, the magnitude 3 earthquake is actually 10 times as strong as the magnitude 2. And so if you go up 1 unit on the Richter scale, you're actually getting 10 times stronger. So like a magnitude 4 would be 100 times stronger than a magnitude 2. So it's a big deal when you get up into the big numbers on the Richter scale. pH is another logarithmic scale. So if we're talking about concentration of hydrogen ions, that's where we get our pH from, logarithmic scale. So something with a pH of 1 is 10 times more acidic than something with a pH of 2. It's like a reverse logarithmic scale. And so they are used. Another one would be like decibels for sound level. Okay, that's a logarithmic scale as well. Human hearing works in a logarithmic manner. Just because something's putting out twice as much energy, we don't hear it as twice as loud. We actually hear most people hear on the logarithmic scale. Okay. So in order for us to perceive that something is twice as loud, it would really have to be putting out like 10 times as much energy for us to perceive it as twice as loud. Okay. Just a little bit of background on why we even care about logarithms. Okay. So we think about the graph, that's kind of enough to give us an intuition that we would be able to find the derivative of these things because we don't have any cusp or any corners or any discontinuities in the graphs of these. The one issue we do have is at 0. So at 0, we're undefined, and we have a situation where we're approaching negative infinity at 0. If anything bigger than 0, we're okay. That's what we're looking at. That's what we're looking at. So we'll just get right to the rules here. The general derivative rule says if we have a log with some base b of x, then our derivative is going to be 1 over x times the natural log of b. So that's kind of interesting. That no matter what base logarithm we have, we can write the derivative in terms of the natural log. You remember what the base of the natural logarithm is? E. It's e. The common log, yeah, is base 10. Yeah, so here natural log is base e. Base e. Okay. But that's maybe not all that impressive. If you can remember, you can change the base logarithms. And there's a little change of base formula you can do and rewrite it in a different base. So. But ln is really convenient for us. It's really nice. We're really not going to have to deal with just generic logarithms too much. Most of the time, we're going to be dealing with natural log here. Okay, so that's the more important one out of these two to have in memory. Okay, so if we have the derivative of the natural log of x, that's going to be 1 over x. Okay, so that's a really important one. Okay? And it'll come up in the things we do down the road. Well, if we think about the chain rule, so like what if we have something inside of our logarithm other than just x, okay, and we get this formula. So in Leibniz notation, it says we want d dx ln of u for u some other function. And then that's 1 over u, that's just this part, times the derivative of the inside, which is du dx. In prime notation, which to me is the easier way to remember it, if we want ln of u, it's 1 over u times u prime. Okay. Or you could combine those and say it's u prime over u. Okay. Writing it this way is nice. We just get the one term all collected together, but it's a little bit more confusing to see how we get that from this thing. Okay, so u prime over u. Okay. Or here they've got it written in function notation for the inside function, so g prime x over g of x. Okay, same thing. So that's our big rule. That's our big rule here. So let's do a couple. Okay. That is the main takeaway in this section, just applying that rule. Okay, so let's see. We want to find y prime given y equals the natural log of x to the third plus 1. So the thing we have inside of our natural log is more complicated than just an x. So we have chain rule involved here. So we need to remember the chain rule version. And it says we're going to get u prime over u. There, 1 over u times u prime. So y prime here. we're going to get on the top u prime, so the derivative of the inside part. What's that going to be? Yeah, 3x squared. Just the derivative of x cubed plus 1. And then on the bottom, we just copy down x cubed plus 1. Something that's a little weird, maybe a little uncomfortable, is that when we take the derivative of something with a logarithm, we don't have a logarithm in our derivative anymore. And so the ln just goes away. That's okay. Maybe feels a little weird. Any questions on that one? See where everything's coming from? Okay. What about, we'll just change our function here. Y prime. Yep, sorry. Uh-huh. Yeah. So the longer way of writing it out, which I really prefer, would be to say we get 1 over u, so 1 over x cubed plus 1 times 3x squared. And then that, if we put it together, is x cubed plus 1. Because you can see the chain rule working here better with it written out the long way. Okay. Well, then this one got natural log of sine x. Okay. So I'll write it out the long way. It'll be 1 over u. So our inside function is the u part. So 1 over sine x times the derivative of sine x, cosine. So here we get cosine over sine. And that's correct. We can actually simplify that a little bit. You may remember what cosine over sine is? Cotangent, yeah. Cotangent, so. If you remember that identity, that simplifies it, but both of those are correct. Sine over cosine is tangent, so cosine over sine is cotangent. All right, so just directly using the rule, not too bad. Yeah, not too bad. You know, of course, it's going to get thrown in with all the other rules that we've dealt with. So we'll do some doing all those. Before we do that, though, let's refresh our memory on properties of logarithms or laws of logarithms, if you want to. I know it's probably been a while for some of you. So we got 3 we're going to focus in on, and really you can make a bigger list, but really any other property you write down after these 3 is just a combination of doing these things. So property number 1 is that if we have a log with some base, doesn't matter what the base is, inside the logarithm we have a product. We can rewrite that. You may remember what we can do. The product inside the logarithm turns into it'll come back to you probably. That's the log of m plus log of n. So if we have a product inside of a logarithm, we can write that as the sum of two logarithms. The base stays the same, so that's not tricky. Number two, same idea, but we have division. So we have the log of m over n. Yeah, we subtract. So that'll be log of m minus log of n. And then the third one is if we have the log of something raised to a power, I'm going to write like m to the r power. Yeah, so what happens is we can take the power inside the logarithm and turn it into multiplication times the logarithm. So log of m to the r power would be the same thing as r times log of m. And these hold for any base. So specifically for us, they hold for natural log. So anytime we have an expression where we've got logarithms, feel free, okay, before you have to take the derivative, feel free to manipulate it any way you want to using these. Sometimes we can make taking the derivative a lot easier if we apply some of these. So let's look at one example here. So maybe we want to find the derivative of natural log x plus 1 over square root of x minus 2. Okay. So bear with me on this one. Let's do it two ways. Okay. Let's take the derivative just like it's written, and then let's use our logarithm properties and take the derivative and see which one you prefer. Okay. So we take the derivative just like it's written. It's 1 over x plus 1 over square root of x minus 2 times the derivative of x plus 1 over square root of x minus 2. So to do that derivative of the inside function, do this part, what do we have to use? Quotient rule. We got quotient rule. Okay. So I'm just going to copy down the first part. Times, and then we do the quotient rule. The order I do that in, and I take the derivative of the top, just 1, times the bottom. So I'm going to write it as x to the 1/2. Okay. Minus the bottom, no, minus the top, sorry, I got out of order, times the derivative of the bottom, so that's 1/2 x to the negative 1/2 over the bottom squared. That look right? Let me double check because I kind of got. x to the, yes, wait a second. Negative, where at? Here. Yeah, so I'm taking the derivative of this piece, right? So it'd be 1/2 and then negative 1/2. If we took the derivative again, it would be negative 3/2, but that one's got the derivative there, so I think. So, yep. Because square root of x. Yeah. Oh yeah, I just rewrote before I did any of this. I just rewrote this as x to the 1/2 minus 2. Yeah. Yeah. No, it doesn't matter in the bottom. Okay. And then let's see if we can clean that up. Okay. So over here, it's x to the 1/2 minus 2 minus 1/2 x to the 1/2 right there. So I'm doing 1/2 x to the negative 1/2 times x gives us 1/2 x to the 1/2 because we have 1 minus 1/2, and then it's negative. And then we do have to do it times 1, so minus 1/2 x to the negative 1/2. Did that help us? Yeah, because let me copy this part. Because on the top, we get x to the 1/2 minus 2 minus x to the, I know that's one's positive, one's negative over there, right? So never mind. We get, all right, so we got x to the 1/2 minus 1/2 x to the, no, yeah, minus 1/2 x to the 1/2. So we get 1/2 x to the 1/2 minus 2 minus, I think we need a couple more 1/2's thrown in there. Okay. So that's me doing this 1 minus 1/2. And then, does any of that matter? I don't see anywhere really that that's going to help us out too much. So probably we can just be happy right here. It's just a big ugly answer. Maybe something cancels out in there somewhere, but I'm not seeing it. Okay. Oh yeah, I do see one thing. Because on the bottom, if we multiply these two things together, we'll have square root of x minus 2 squared over square root of x minus 2. So one of those will cancel. But that's not all that life-changing thing. So that's one way. Did a deal with quotient rule, and it's really messy. Let's write it down again and do it using our properties of logarithms. Okay. So what do you see we can do with our properties of logarithms? Yeah. We can say that's ln of x plus 1 minus ln of square root of x minus 2, and I'm going to just write it x to the 1/2. To me, that's a lot easier. Because what's that going to be? That's going to be 1 over x plus 1 times the derivative of x plus 1, which is just 1, minus 1 over x to the 1/2 minus 2 times so that thing we had before is equivalent to this. But to me, that's a lot easier to get there. And we could probably there's probably something you do to clean up a little bit, but that's okay. For sure, we can get rid of our 1 over here. And then we could what else? Well, we can clean up a little bit. Let's see. So we have a half on the top, so we get a complex fraction, and then we have square root of x times square root of x minus 2 in the bottom. We could get rid of the complex fraction if we had to. So this one I moved down to the bottom. Still, to me, that's much nicer than that. That's quite a mess there. It should be the same thing. So, and we didn't even have to do quotient rule. So, anytime we get out of doing quotient rule, I'm pretty happy. Right. Let's think about this one. This one's not like a big, long, messy one. It's just a kind of informative example here. We want to find the derivative of the natural log of absolute value of x. So one reason why a function like this comes into play is if you just have, if we just have natural log of x, what's our domain? Remember logarithms? I can help you. 1 second. Yeah, so our domain there, 0 to infinity. Really, and we're not taking 0. We're undefined at 0, so our domain there would be 0 to infinity. If we stick the absolute value on there, then the only thing we're missing so now negatives become positive, so we're okay. So then we just have one value where we're undefined. So you do come across these absolute values inside of logarithms. They can be really useful to be able to use negative x values as part of our domain in a function. Okay, so let's think our way through this one. Okay. We really got two cases. We can think about this function as a piecewise function. It'd be ln of x if x is less than or equal to 0. Or just less than, sorry. And then, no, sorry, greater than. I don't know what I'm thinking backward because we want positives. I want positives. Sorry about that. Okay. And that's F. I'll get there in a second. Nice. And then what if it's the other way? What if how do we find that? We would do ln of negative x. Huh? We throw the minus sign in, and that makes it positive. It's the same thing the absolute value does. Okay. So that's really what we're doing when we're talking about absolute value of x inside the logarithm. Okay. So for the derivative, we've got to think about both pieces. So if x is positive, that's just business as usual. What's our derivative going to be when x is positive? Just the derivative of ln of x, 1 over x. Okay. If x is negative, we've got ln of negative x. So our derivative would be 1 over negative x times the derivative of negative x plus the derivative of negative x. Negative 1. Okay. So this thing is just 1 over x. What's the bottom turn into? Well, we got a negative 1 over x times negative 1, so we just get 1 over x. Okay. And let's do the last case we can do. It was if we could figure out what the derivative would be at 0, then we can differentiate this thing anywhere. So let's do that last part graphically. Just look at the graph. We won't prove it. If the Wi-Fi works. We want ln, where's it at? The absolute value of x. So can we get the derivative at 0? What's that? Looking at the graph. Yeah, it would be negative infinity. Because of that, we could say does not exist, the two-sided doesn't. I mean, because we're going toward negative infinity. So you can think about it either way. You can either say we don't have a number we can put on it, or you could say negative infinity on that. So we don't get the super nice conclusion. Okay. But what we do get, and we've come up with a derivative formula. Okay. That's that d dx ln of the absolute value of something equals 1 over x for all not equal to 0. Okay. If x is equal to 0, we have other issues anyway, right? Because we get 1 over 0 here. So that's nice. Okay, that's nice to keep note of. If you have absolute value of something inside the natural log, you still get 1 over x. Doesn't change it. Okay. So all right, let me go a little bit out of order on the slides here. We don't have too much left. Okay. Let me go a little bit out of order on the slides. I want to save the logarithmic differentiation for last. Here, we don't have problems related to this. This is just something for us to ponder. Okay. So we've seen E defined one way in this class. We've seen E defined as the base of an exponential whose limit as x approaches 0 is 1. We've seen that. So here we're going to get another definition. You can look at the details if you want to. The main takeaway here, okay, is what we end up with there. So here's our next slide. This gives us another definition for E. We could say E is the number when we take the limit of 1 plus x to the 1 over x power as x approaches 0. That's E. Okay. You'll see it that way occasionally. The more common way, you'll see the same thing expressed. It's like this. You'll see this definition for E quite a bit. That inside will have 1 over n and then raise it to the n power. Okay. That's just substituting n for 1 over x. And then we let n go to infinity. Anybody recognize this from any kind of formula? Okay. You may not. Depends especially if you took pre-cal somewhere other than here, you may not. So in pre-cal, one of the exponential formulas we talk about is compound interest. Compound interest. And if you have a continuous compounding interval, if we say we're going to take the limit of how often we can compound the interest, we get e to the, we get p e to the RT. So E comes out of that there. There's one place. Okay. Comes up a lot. There's just an alternate definition for E. There are tons of ways you can define E. It pops up all over the place. You will. How many of you have to go on and take Cal 2 that you know of? Okay, so you'll see some more definitions for E. Okay. You can define E as what's called a continuing fraction, where you got like 1 plus 1 over 1 plus 1 over 1 plus 1 over 1. That way. You can write out a definition for E with that type of thing. One way. And you can also define E as like a infinite series. Not define E as an infinite series too, so you'll see that. All right, so that's out of the way. Now let's go back. So here is something we want to differentiate. I'm just going to copy it down and we'll go over and do it on the scratch paper because I think it's easier to follow if we're writing it down as So differentiating a function like this, where we've got a pretty complicated expression with a bunch of exponents and multiplication and division involved, we can use a technique that we're not going to focus on too much. I'm going to go ahead and write square root as 1/2 power, just because it's really messy. And you really don't have to use it all that often. But when we have something like this we're trying to differentiate, it can be really useful. Remember we said that if we use the properties of logarithms to rewrite stuff before we try finding a derivative, then it can make our life a lot easier. Now we had that earlier example, so here we're extending that idea. Okay. So the idea behind what gets called logarithmic differentiation is that if we have something really complicated like this, we have an equality, right? So if we do something to one side and we can do it to the other side and it stays balanced. So here what we would do with logarithmic differentiation, okay, I don't think, maybe I gave you one simpler one in homework. I have to double check. But this is not that big of a deal for us to do. Okay, this would be like in bonus problems. I just want you to see it for the most part. Okay. Idea behind logarithmic differentiation is that we can take the log of both sides, and then we can leverage all those properties of logarithms to make this thing easier to deal with. So you can take any log you want to, but the nicest one for us to work with is natural log. So what we would do is we would take the natural log of both sides. Okay. Really the only downside to doing this, and it's not much of one, okay, is that now when we take the derivative of the left side, we've got to do implicit differentiation. We've got a y over here. Okay. But that's really not that big of a deal, because the natural log, implicit differentiation is just the chain rule, thinking that y is a function of x. And so over here we'll have 1 over y times y prime. So not that big of a deal. So let me back up just for a second, because let's use our properties of logarithms before we start getting into this. What can we do? We've got a product and then division, so we can split that thing apart. And we can call this natural log of x to the 3/4 plus natural log of x squared plus 1 to the 1/2 minus natural log of 3x plus 2 to the 5th. Okay. Yeah. You just have to make sure the order of operations works out. This one we don't really have anything to be concerned with, because like we put these together to be this times this and then divided by this. So if we had had a product in the denominator, you would just have to be careful to put like a bracket after your minus whatever's in the denominator. Yeah. You had to make sure that the order of operations are working, but we're good here. So then what else can we do? We can do something else that's nice. We got another property of logarithms. Yeah, all those powers we just move out front. So that really helps, because then we just use our constant factor rule. Now taking the derivative is much nicer than having to deal with product rule and quotient rule all together. So if we go to take the derivative of both sides, this side is just 1 over y times y prime. Implicit or chain rule, if you want to think about it that way. This side, this is just a constant multiple, so it's just 3/4 times whatever ln of x is. Ln of x is, derivative of ln of x is 1 over x. Yep. Plus 1/2. Our derivative here would be 1 over x squared plus 1 times the derivative of x squared plus 1, which is just 2x. So that's u prime over u, that's how I'm writing that. Minus 5 times, again, we got 1 over 3x plus 2. And then the derivative of that is 3, so u prime over u. We didn't have to use product or quotient rule in there, so really nice. We just have just a little bit of work to do. So here that's 3 over 4x plus, these 2's cancel. So plus x over x squared plus 1. And then minus 15 over 3x plus 2. The only real hassle that we've created by doing this is that we need to solve for y prime. That's not a big deal because the only thing we have to do to solve for y prime is multiply both sides by just y. Yeah, because y over y. Yeah, so just multiply both sides by y. So y prime is y times what we had. And then really, we don't even have to deal with our derivative having both x and y involved because we have an explicit expression for y we can substitute in. Our explicit expression for y is this. So we stick that thing in where y is, and we don't even have two variables in our derivative. So final answer with, in terms of only x, so explicit derivative. It's kind of ugly, but I really don't want to imagine having to get it using product and quotient rule. So there's y times, yeah. And it's long, but we really didn't have to work hard. So I haven't done it, but I just imagine trying to come up with this using product, and then we're going to have a quotient rule with a product rule inside of it, and then we get chain rule in there, right? Because like when we need to take the derivative of this one, we get chain rule, so chain rule on this one. Nightmare that's turned into not being that bad with logarithmic differentiation. We don't have to make use of it very often in practice, but it's a really good technique when it calls for it. And also, we kind of mentioned this earlier, but even though we took the natural log of both sides, we don't end up with any logarithms either. So it's another good thing about it. We don't introduce logarithms into a problem that doesn't have them. We use them, but they go away when we take the derivative. All right. Questions? Think of anything? All right. That's it then. I think what the trig rule assignments due tonight?